Today's learning goal is to apply Newton's second law. Apply Newton's second law. Okay, so let's take a look at this new example. This is an example involving friction on a level surface. It says, a car skids to a stop on a wet level road. The coefficient of kinetic friction between the car's tires and the road is 0.20. The car has a mass of 1,500 kilograms. Find the car's acceleration. Okay, so again, we're going to follow the same steps that we've been following. We're going to start by drawing a free body diagram of all the forces acting on this car. So let me go ahead and show this is the road. Here's the car, which I'm going to represent just by a simple shape, like a rectangle. And I'm going to go ahead and draw all the forces acting on this car. You try it first. Pause the video now. Okay, hopefully you tried it. Let's go ahead and take a look at the solution. So the forces acting on the car are the weight of the car pointing straight down. That's the force of gravity acting on the car. We've got the normal force. So the surface is holding the car up, keeping it from falling through the ground. The normal force always points perpendicular to the surface. So in this case, since the surface is horizontal, the normal force will point up. And then there's also a force of friction, kinetic friction in this case, since the car is moving, which opposes the motion of the car. So if we say that the car is moving to the right, then the force of friction will point to the left, slowing the car down. So force of friction, like that. Okay, next we should select our x and y directions. I think here, again, it makes sense to keep y as the up and down direction and x as the side-to-side direction. We want the majority of the force vectors in our diagram, as many as we can, to point completely in the x and y direction. So in this case, since all the forces are 90 degrees with each other, we'll just keep pointing up and down and side to side like we usually do. We should also ask ourselves, what are the accelerations? So what's the acceleration in the x direction? What's the acceleration in the y direction? So in the y direction, the acceleration is 0 because the car is not speeding up or slowing down. In the y direction, it's not bouncing. In the x direction, there is an acceleration. The car is slowing down. It's coming to a stop. We don't know that acceleration. They're asking us to find it, so we're going to leave this as a question mark. Next, we have to write a table of the x and y components for each of the forces that appear in the free body diagram. Okay, so you go ahead and try it first. Pause the video now. Make a table of the x and y components of each of the forces in the free body diagram. Okay, hopefully you tried it. Let's take a look at the solution. So the normal force is pointing in the positive y direction. So it's a 0 component in the x direction, and the y component is positive n. The weight points in the negative y direction, so its x component is 0, and its y component is negative mg, because mg is the magnitude of the weight. And we have a little negative out in front because it points in the negative y direction. For the force of friction points in the negative x direction. So we're going to have a negative x component, and the y component of the friction is 0 because it points completely in the x direction. The friction is calculated as the coefficient of friction, mu k, times the normal force. Again, negative sign out front because it points in the negative x direction. Step 3, let's apply Newton's second law. You go ahead and try it first. So add up the forces in the x direction, set it equal to mass times acceleration in x. Add up the forces in the y direction, set it equal to mass times acceleration in y. Pause the video now. Okay, hopefully you tried it. Let's take a look at the solution. So 0 plus 0 plus negative mu k n are our forces in the x direction added together. So that comes out to negative the coefficient of friction times the normal force. It's going to be mass times acceleration in the x direction. We don't know the acceleration in the x direction, so we're going to leave it as acceleration x. In the y direction, we have normal force plus negative mg plus 0. So add those together. Normal force plus negative mg plus 0. is going to be equal to mass times acceleration in the y direction. Acceleration in the y direction is 0, and 0 times any number is 0, so this is going to equal 0. Okay, so our equations are set up. Step 4, we are going to solve the system of equations. Pause the video now, try step 4 on your own, solve the system of equations, go. Okay, hopefully you tried it on your own. Let's go ahead and solve the system to see the solution. So my strategy here is going to be to first solve for normal force, and then substitute that normal force into the other equation to find the acceleration. The mass of the car is 1,500 kilograms. Little g is positive 9.8. 1,500 times 9.8 is 14,700. And add 14,700 to both sides to get that the normal force is 14,700 newtons. Okay, so we're going to substitute that in to our other equation to solve the system. So let's take a look. We've got negative mu k. Mu k we were given. Mu k is 0.20. So mu k is 0.20 times the normal force, which we just found, 14,700 newtons, equals the mass of the car, 1,500 kilograms, times the acceleration along the x direction. So in order to solve for acceleration, we should divide both sides of the equation by 1,500. And let's see what this comes out to. So the acceleration in the x direction is negative 1.96 meters per second squared. Let's see if it makes sense. So negative 1.96 meters per second squared is our acceleration. We've got a negative acceleration. The car is moving to the right in the positive x direction. Negative acceleration means that the car is slowing down. So that makes sense to get a negative answer. All right, let's take a look at this new example. So example 4, a penguin on a sled with a mass of 5 kilograms. So the penguin and the sled together have a mass of 5 kilograms, is pulled at an angle of 30 degrees above the horizontal as shown in the figure. So take a look here at the figure. Find the force needed to pull the penguin at a constant speed given that the coefficient of friction is 0.10. So we're going to start by drawing a free body diagram. Pause the video now, give the free body diagram a try. Okay, hopefully you tried it. Let's go ahead and take a look at the solution. So here's the surface on which the penguin and sled are sliding. I'm going to represent the penguin and sled together as of just a box, a simple shape. And then I'm going to draw all the forces acting on the penguin sled system. So we've got the force of gravity pointing straight down. We call that the weight. We've got the force normal pointing perpendicular to the surface. So since the surface is level, the force normal will be pointing up. There's a pulling force. Presumably this could be like a rope or something like that. So I'm going to call it tension. We've got a force of tension pulling at an angle of 30 degrees above the horizontal. And they gave us a coefficient of friction. So there's a frictional force that's acting opposite the motion of the penguin. So that would be backwards and parallel to the surface. So something like this. That's a force of friction. Next, let's pick our coordinate system. So we want our x and y directions to line up with the majority of the forces in our diagram. So notice here we've got tension, which is pulling at an angle, but 3 of my forces are perpendicular to each other. So I'm going to line up the x and y directions with those forces so that at least 3 of my force vectors point completely in the x and y directions so that I can make the problem easier for me to solve. Right, I'm going to have to find x and y components of the forces that are not pointing directly in the x or y direction. So it makes sense to only have one of these forces not completely along x or not completely along y. So in that case, it would just be the tension. Okay, and then last I'm going to consider the acceleration. So what is the acceleration in x? What is the acceleration in y? Well, the penguin isn't jumping up or down. It's not speeding up or slowing down. In the y direction, they're asking us for the force needed to pull the penguin at a constant speed. So I'm going to say that my acceleration in the x and y directions are 0. The penguin is moving at a constant speed. Okay, last, I know that I'm going to have to resolve the tension vector into x and y components to do the next step, so I'll just go ahead and do that now. We're going to try to imagine this like little red triangle that fits underneath the tension vector. Right, and I don't have a lot of room here in my diagram, so I'm going to go ahead and redraw that triangle off to the side so that I can resolve the components of the vector. So the magnitude of this vector is capital T. This angle here between the tension vector and the horizontal direction is this 30 degrees. So I need to do some like trig analysis of this triangle to try to figure out, okay, what are the x and y components of the tension vector? So the adjacent side of this triangle, since it's a right triangle, we're going to use the cosine function for the adjacent side. So it's going to be the magnitude of the angle, or sorry, the magnitude of the vector times the cosine of the angle for the adjacent side. And for the opposite side of the triangle, the y component of the tension vector, we've got the magnitude of the vector times the sine of the angle. And just as a reminder for myself so that I don't forget, the adjacent side is the x component here in my diagram. So I'm going to remember that this is tx. And the opposite side of this triangle represents the y component of the vector. That's how much the vector points along the y direction. So this is ty. I'll just remember that. I'll like write a little note for myself. Okay, so you go ahead and make the table of the x and y components of each of the forces. Remember, look at the free body diagram in order to figure out what are the x and y components of each of the vectors that appear in the free body diagram. Pause the video now. Okay, hopefully you had a moment to try that. Let's go ahead and look at the solution. So we've got that the normal force points in the positive y direction. So we've got the x component of the normal force is 0. The y component of the normal force is positive n. The weight points in the negative y direction. So its x component is 0. Its y component is negative m times little g, because m times little g is how we calculate the magnitude of the weight, and a little negative sign in front because it's pointing in the negative y direction. The force of friction is pointing in the negative x direction, so its y component is 0, and its x component is negative because it's pointing in the negative x direction. Negative mu k, the coefficient of friction, times the normal force. This is how we calculate the magnitude of the frictional force. And last, we've got tension, the x and y components of the tension. We just found them using sine and cosine. So I'm going to go ahead and put those here in my table. The x component is t cosine 30 degrees. The y component is t sine 30 degrees. And I should double check the signs on these. So let's take a look. So tension points in the positive x direction, positive y direction. So positive, positive, that makes sense. Okay, let me move on. So step 3, go ahead and apply Newton's second law. Add the forces in the x direction, add the forces in the y direction, make it equal to mass times acceleration in x and y. Pause the video now. Okay, so let's take a look at how you did. We've got in the x direction 0 plus 0 plus negative mu k n plus t cosine 30. So that's negative mu k n plus t cosine of 30 equals mass times acceleration in the x direction, which we said was 0, so mass times 0. In the y direction, we've got normal force minus mg plus 0 plus t sine 30. Equals mass times acceleration in y, which we said acceleration in y is 0, so mass times 0. This will come out to 0. This will also come out to 0. Okay, and now we have our two equations. We should solve the system of equations. So step 4, go ahead and solve the system of equations. Give it a try. Pause the video now. Okay, so for step 4, solving the system of equations, I'm going to start by solving for the normal force, and I'll substitute that into the other equation. So let me try that. I'll add mg on both sides of this equation, so normal plus t sine 30 equals mg. And then let me subtract both sides of the equation by t sine 30 to get normal by itself. And then I'll go ahead and substitute that into my other equation. And let's see what we got. So we've got negative mu k, open parenthesis, I'm substituting this in. So instead of writing n, I'm going to write mg minus t sine 30 because that's the same thing. Plus t cosine 30. Next, I should distribute mu k into the parenthesis. So negative mu k mg minus mu k t sine 30 plus t cosine 30 equals 0. And then I'm trying to solve for the tension, right? So I should collect like terms. So I'm going to move the term that does not have tension in it over to the other side of the equation by adding mu k mg to both sides of the equation. Next, I'm trying to solve for tension, and both of these terms have tension in it. So I'm going to factor out tension. Okay, I actually know a lot of these things, so let me start substituting in values. So tension, open parentheses, negative, mu k, the coefficient of friction, we were told is 0.1. Again, mu k is 0.1 times the mass of the penguin and sled, which was 5 kilograms, times little g, which is 9.8. So let's put all these things in the calculator. So all this inside of the parenthesis comes out to 0.816. There's more numbers. I'm rounding a little bit. And then 0.1 times 5 times 9.8 comes out to 4.9. And 4.9 divided by 0.816. Gives us, right, so divide both sides by the 0.816. We get that the tension is about 6 newtons. So in other words, we would need to pull the sled with a force of 6 newtons in order to get the penguin moving at a constant speed, constant velocity. Okay, great job. It was a little bit intense, but we just followed the steps, right? So starting with the free body diagram, being very careful, resolving the tension into its x and y components using sine and cosine, filling out our table, writing Newton's second law, applying it by adding the forces in the x direction, adding the forces in the y direction, setting it equal to mass times acceleration. And then step 4, which is maybe the most challenging step, was solving the system. And our strategy was to solve for the normal force and in one of the equations and then substitute it into the other equation. And then just sticking with it until we have our final answer. Okay, great job.